So this video is on finding a power series representation for one function by either differentiating or integrating another function and then ultimately finding the interval of convergence. And recall the theorem that basically says that if you have a function and you integrate it on an interval of convergence, if you have a power series and you differentiate or integrate it on an interval of convergence, that it actually converges specifically to that derivative or to that integral on that interval of convergence for interior points only. So we would need to test endpoints. So let's go through the process of finding a power series representation. And in this case, the given example is g of x is ln of 1 minus 3x, and we're going to use f of x. So we're going to go from f of x to g of x, either through the process of differentiating or integrating. So let's look at this and figure out which way we need to go, either integration or differentiation. And looking at f of x, and if you can't see that if you integrate f of x, you'll get a form of g of x or a multiple of g of x, then you should just go ahead and do both. All right, so I'm going to start with integration because I can see that if I integrate f of x, I'm going to get a multiple of g of x. So use substitution, and you get the integral minus 1/3 of du over u. And that's just simply minus 1/3 ln of u, and then back substitute, and you see that you get something that looks like g of x, except it's a multiple of it. In fact, it looks like the integral of f of x is equal to negative 1/3 times g of x. So if I solve for g of x, I get g of x is equal to negative 3 times the integral of f of x. So this is important right out of the gate to see what the relationship is between f and g. So where I would proceed next is to work with f of x. And f of x, which equals 1 over 1 minus 3x, is a geometric series. And it's a geometric series with x equaling 3x. So this converges when the absolute value of 3x is less than 1. So solving that inequality, you get negative 1/3. X is between negative 1/3 and 1/3. So let's we're going to approach this in two different ways. The first is going to be expanding the summation for f of x and then actually integrating each term. So let's go down that path first. F of 3 of x is simply 1 plus 3x, and all I'm doing is just expanding the series out, the geometric, and then I'm going to integrate term by term. Right, and that continues. So now I'm going to integrate both sides. So integrate both sides. And I'm going to pull off to the side a little bit of work so that you can see what's going on here. Let me grab another ink. So the integral of 1 is simply x, and the integral of 3x, right, is simply the integral of 3 times x, which is 3x squared over 2, right, plus a constant. And the next term, which is the integral of 3x squared, I just pull out the constant, and this is 3 squared times the integral of x squared, right, which is just 3 squared x cubed over 3. Okay, and you can continue on down with the pattern. The integral of 3x cubed is equal to, pull out the constants, right? So 3 cubed x to the 4th over 4. And you're going to continue integrating term by term, right? And these all have a constant added onto them. So this term is simply 3x squared over 2. This term, when integrated, is 3 squared x cubed over 3. And this term is 3 to the 3rd power, x to the 4th over 4. And you can guess this one is 3 to the 4th, x to the 5th over 5, and that continues. So we integrated both sides. And so this is the expanded series of the integral of f of 3x. So this is the integral of f of 3x in expanded form. Now, I was asked to find a power series representation for the new series by integrating or differentiating f of x. And so now I need to look at this expanded series that I just integrated term by term and come up with summation notation. So that's why I left the powers of 3 intact, so we can sort of see what we have going on here. So we'll have to, this is guess and check to some degree. Right, I'm going to start the series at k equals 1, and the reason why I did that is I see that I have a 3 raised to a power, and it's always 1 behind what the power of x is. So it's 3 to the k minus 1 x to the k over k, right? And how I came up with that is that k, whatever k is, you're dividing it, and it's the same as the power, right? So you can see a pattern emerging, and that's what we're looking for here. This is more akin to what we did with trying to come up with explicit formulas, right? You're trying to notice a pattern of what's going on here, but certainly you should check it and make sure that it generates it. So when k equals 1, 3 is raised to the 0th power, x to the 1 over 1, and that's simply x. So it generates the first term. When k equals 2, let's see if we get the second term. We get 3 raised to the 1st power, x to the 2nd over 2, and indeed it does. So this is the power series representation for the integral of f of 3 of x. Now, we know from the original relationship that g of x is equal to minus 3 times the integral of f of x. So let's just drop in what we know. This is minus 3, and the integral of f of 3x is right here. So let's drop that down into here and clean it up a bit. So this is k equals 1 to infinity, 3 to the k minus 1, x to the k over k. So one thing I can do is bring the 3 in side the summation, and I get negative the sum from k equals 1 to infinity, 3 to the k, x to the k over k. And the only thing here that remains, the only thing else I can do with this summation is just combine this. So here is your power series representation for g of x. So that's the first part of the issue. So this is the power series representation for g of x found by integrating f of x. And by the theorem, this is where the theorem comes into play. By the theorem, I that was defined for f of x is defined for the interior of g of x. So the interval of convergence here, based off of that theorem, is -1/3, x greater than -1/3, but less than 1/3. But it doesn't guarantee the endpoints, right? This is only for interior points of I, so we need to test the endpoints. Excuse me. So let's go about and test the endpoints. I'm going to start a new page here. So testing the endpoints involve putting in x equaling -1/3 and 1/3 into the new power series representation for g of x. So I need to test the individual point, the individual endpoint. So let's put it directly into the new series that we just generated. And this is 3 times -1/3 to the k over k. And we end up with a alternating harmonic, which we know converges. So that's an alternating harmonic which converges. And when x is equal to 1/3, we end up with a divergent harmonic. So the interval convergence is -1/3 inclusive to 1/3 not inclusive. So that is how you use the theorem and integrate term by term to get g of x. Now I want to take you down another path. I'm going to draw a line here. And we're going to start with the relationship that we established up front. That work is still required. And we know that if we integrate f of x and multiply it by -3, we get g of x. So now I want to go down the path of simply manipulating the series, the power series, its power series representation itself. So this is the integral of f of x. And I'm going to loosely mix this notation, but again, it's very loosely. So I'm going to manipulate the power series directly. So I'm going to rewrite it a little bit so that I can get at this thing a little easier. And I'm going to split off. K gets applied to both of these factors. So this is 3 to the k, x to the k. And now recognize that 3 to the k is simply a constant. So when we integrate, we take that constant outside, right? And then what remains for us to integrate with respect to x is x to the k. So this is equal to the sum from k equals 0 to infinity, 3 to the k, the constant comes along for the ride, x, and when we integrate, we add 1 to the exponent, and we divide by that exponent. So we're left with this. Now, one thing that, okay, so this is the integral of f of x. So now I want to go back to the established relationship that g of x is equal to -3 times the integral of f of x, which is now the new summation that we just came up with, 3 to the k, x to the k plus 1 over k plus 1. So now I can bring the 3 inside, and I get from k equals 0 to infinity, I get 3 to the k plus 1, x to the k plus 1 over k plus 1. So now what I can do is I can subtract 1, and so subtract 1 off of all of the k's, and then add 1 here, right? That's the equivalent. So this series now becomes k equaling 1 to infinity, and it is 3x to the k over k. And this is exactly what we arrived at when we integrated term by term. All right? And then you would have to go and test the endpoints. So this is another way of solving this problem. Okay, that's about it for this video.